The last type of distribution I'd like to discuss in this lecture is the volumetric charge density. When a charge is really dispersed in a volume, it occupies like a cloud of electrons or cloud of protons in a certain volume. And we'll discuss a very simple classical problem, which is calculating the field resulting from a sphere that is charged with a volumetric charge density rho v coulomb per meter cubed. And here there are a number of things to notice in this diagram here. This is my observation point. We assume it is along the z-axis at a height of z. So it has x equal to 0, y equal to 0. We divide, as we did before in our previous examples, we divide the volume into small differential elements. Here we have a differential volume element. So this is the one that we have here. And it is dv, and the coordinates, as we agreed for any source point, will be r dash, theta dash, and phi dash. So this is the theta dash, it's the angle from z-axis, rho dash is the distance from the origin, and of course every element within this volume will have its rho dash, r theta dash, r dash, and phi dash. Now there is a very important angle we'll need, is this angle alpha. It is the angle between the line connecting that element to the observation point and the z-axis. So this angle alpha is extremely important, as you see in our calculations. Now the way we do this, of course, is that we divide the element to volumes. We apply the expression for the electric field of a point charge. If every volume is small enough, then we consider it to be like a point charge. We calculate the distance squared from that element in the volume to my observation point. We calculate the unit vector pointing from that element in the volume to the observation point. So we need a unit vector along this direction. And then we do summation over all these elements in the volume to get the total field at my observation point. Few things to remember. It's a volumetric charge density. Then the charge of any small volume element dq is equal to rho v, which is volumetric charge density coulomb per meter cubed multiplied by the volume. The volume, as we have seen before in spherical coordinates, is rho squared sine theta dr d theta d phi. And all these dashes, and I explained earlier, they are used to tell you that these are the coordinates of the source, the coordinates of the charges. So there is a difference between the coordinates of my observation point, which does not have any dash, and the coordinates of my source point, where the charges are. So we have to put these dash. Now the vector AR, the point, this is R is pointing from here to here. So AR is a unit vector in this direction, and we need to decompose the unit vector here for reasons that become clear later. So this one here is, this angle here is 90 degrees. So this AR can be decomposed into, you have here a component along the Z direction. So if this is AR, it's pointing towards the observation point. It will be decomposed into two vectors here. So it will be decomposed into two vectors, trying to blow them for you here. So this is one component, it's red, okay? And this is another component here. So this is how this AR will be decomposed. And you could see here from this one that the AR has two components, cosine phi in the Z direction and the sine phi in the rho direction. Sine phi actually in the direction of rho. So this one here, we will not need to worry about it, and I'll explain to you why. Because of symmetry, if you have an element, a volume element in this point, there is another volume element that corresponds to it in the volume as well, where the two fields component actually do cancel each other out. So I can draw here another volume element here, okay? And then if you try to find the field resulting from this element, you will see that it will cancel in the rho direction. The rho directions will cancel, so the field, the component here and here will cancel each other out, and you're left only with the Z component. So this problem will not have any rho component as long as you're talking about the field outside that sphere. So we can now proceed to say, okay, there is only a Z component, and we can do our calculation here. We can simply say that this is the total field that we are looking for. We are integrating the contribution coming from every element. What we did here, we put rho v over 4 pi epsilon naught coming from here, and then what I did, I kept only the z component, as you could see here. So I have here cosine phi in this expression. So what remains is simply mathematics, how to do this integration and how to substitute for cosine phi in this expression. There are two identities that we'll need to continue this integration. The first one is coming from the expression for the cosine. So we know that in this triangle here, the r dash, r, and z triangle, r dash squared is equal to r squared plus z squared minus 2rz cosine alpha. This will give me an expression to use in cosine alpha. I have to get rid of this cosine alpha here in the integral. The second one, because I'll be integrating over the volume, I would like to express sine theta as well. So sine theta here, as you could see, sine theta dash, this angle here. Again, from using the cosine triangle rule, we can simply say that this length of this vector squared is equal to r dash squared plus z squared minus 2zr dash cosine theta dash. This enables me to get rid of sine theta dash as will become clear later. What we will do is that we will focus on the contribution coming from a certain phi. So I will get the contribution coming from a slice of this sphere. And in that case, the field only depends on r dash and r. We'll see how we can try to put these integrals in this form. So we start to put all the elements together. I explained to you from the cosine integral. Cosine alpha is given by this expression. This is from called the cosine rule for triangles. Cosine theta is given from this one. And because I'm talking about one plane only, so phi is a constant. If I change theta by a certain theta, d theta here, then this will result in the change of the distance r by dr, small amount dr, okay? And this, of course, keeping r dash constant. So I'm trying here to talk about another element to the observation point. So if r dash is r dash small skips constant, then the change in cosine theta, we can differentiate both sides, keeping r dash and z constants. In that case, you can see this is the expression that you will get. Where do I get this one from? Because I'll be integrating over using r dash and r, and these two are independent. If I'm talking about one slice of this sphere, at a certain phi. So now I'm all set to do the integral. I can get rid of cosine alpha by this expression. I can get rid of sine theta that's coming from the volume differential volume expression from this one here. I can integrate theta. I can make theta goes from 0 to pi, and if theta goes from 0 to pi, you'll see something very interesting, that the length r from my observation point from my field point to the observation point will change from z minus r dash z plus r dash. Where did this come from? If theta is equal to 0 and you have this r dash, this will be your point here, okay? So this one here is r dash, and the distance r is this one. But this r is equal to the total z minus this length here, which is simply equal to r dash. So the distance r between my field point and my observation point is equal to z. In other words, r dash plus r, when you sum these two, you get z. The other way around, when theta is equal to pi, then your point is somewhere here in the sphere. So this is now your r dash, this r dash. So the distance r from this point, from the element here to my field point up there is equal to z plus r dash. So here we are making r, the capital R, will actually replace theta dash in our integral, and the r dash will still be a variable of integration. So now we know that a theta goes from 0 in the z-axis to pi in the minus z-axis. The distance from my observation point will go from this one, this small distance, which is z minus r dash, to this big distance, which is z plus r dash for every r dash. So now we'll do a change of integration. We'll change from the integration over r dash, theta dash, and phi dash to an integral over r dash, r capital, the distance, and phi dash. So after simplifying this, what we'll end up with, notice what are these terms. This is cosine alpha. This cosine alpha we talked about before. This one here is sine theta dash d theta dash. So we replaced it, it's this term here, this part here, sine theta dash d theta dash. We replaced it in terms of r and dr. This one here is coming from Coulomb's law. We have to divide by 1 over r squared. This one is coming from the volume integral. Remember, the volume element is r dash squared sine theta dr dash d theta dash d phi dash. Now we removed theta, we got rid of theta. So now we are integrating over r from z minus r dash, z plus r dash. And we'll span the whole radius of the sphere to sum the contribution from all elements from 0 up to a. And phi, because we took only one slice, phi will be integrated from 0 up to 2 pi after that. And I took the rest of the terms out, the constants out. Notice here I'm keeping only z components because I explained earlier the root components will cancel out. What remains is simply to simplify. So I did the integral relative to phi, I multiplied by 2 pi, and this will cancel with 4 pi here, and you get another 2 from here, so you end up with 4 only in the denominator. And then we will divide the denominator here by r squared, so end up with 1 plus z squared minus r dash squared divided by r squared. These are all simplifications. I will first integrate relative to r capital, and then I will integrate relative to r dash. If you integrate 1 relative to r capital, you get to r. If you integrate 1 over r squared, you get minus 1 over r. So we substitute for that, and we substitute for the upper limit and the lower limit in order to be able to span the whole expression. As you can see, this integral is not easy to apply. And later we will see an easier way to obtain this integral. We'll talk about something called Gauss law, and Gauss law makes solving problems with high degree of symmetry way easier. Right here we had to go through very cumbersome integrals, but I don't really ask you to memorize these derivations, just to understand them and understand how to use the final result. So now we are ready to integrate r and substitute for the upper limit minus the lower limit. So if you do a substitution here, you get z minus plus r dash upper limit minus z minus r dash. So this one will give you 2r dash. The same thing will come from here. Substitute upper limit, you put r here equal to z plus r dash, and then minus r here equal z minus r dash. Take into account there is a negative sign. You will see that this whole bracket will give you 4r dash. As the z will cancel out. And you end up here with r dash multiplied by 4r dash, then you get 4r dash squared. Now we can integrate r to cover the whole sphere from 0 to a. The integral of r dash squared will give you r dash cubed over 3. You put the radius of the sphere, which is a. You get 4 over 3. I multiplied by pi. I divided by pi for a reason become obvious for you right now. And I move this row volumetric into this part. What is this expression here? This is the volume of the sphere. This is the uniform volumetric charge density. So when you multiply these two together, you get the total charge within that sphere. If you multiply the volume of the sphere by the uniform volumetric charge density, you get the total charge within that sphere. We call it here capital Q. So now we know that the expression for the electric field, it will be in the z direction. It will have value of q over 4 pi epsilon naught z squared. But remember, we are the one who determines z. We determine z to be in the direction connecting from the center of the sphere. This is my sphere, I'm sorry for not very accurate, but to my observation point. But I could have selected z to be in this direction or that direction. So in general, the field will be pointing actually in the r direction, where r is the direction pointing from the center of the sphere in the outward direction. And we call the distance between the center of the sphere to the observation point, but we don't call it z anymore, we call it r. So what does this tell us? The field outside a uniformly charged sphere is given by the total charge within that sphere divided by 4 pi epsilon naught r squared, where r is the distance between the center of the sphere to my observation point, and ar is the unit vector pointing from the center of the sphere to my observation point. But what does this remind us of? If you remember, this is exactly the same expression for a point charge of value q at the center. So this remarkable result is telling you if you have a sphere of uniform charge outside the sphere, the field looks as if the charge is a point charge concentrated at the center. So this is exactly the same expression that we had from Coulomb's law when we took the point charge. So the point charge, so it looks as if the whole charge inside the sphere, which is really uniformly distributed, as if it is focused at the center. It's only a point charge. This result, I ask you to remember, if you have a uniformly charged sphere as shown here, the field at any point outside the sphere, is pointing in the radial direction from the origin to the observation point, and its value is q over 4 pi epsilon naught r squared. R is the distance between the center to the observation point, and the AR is the unit vector pointing from the center to the observation point. So this makes the case of handling a uniformly charged sphere is easy. Now, if I give you another example where the charge is not uniform, you have to go through the derivation to determine the total field here. Let's see an example here. In this case, I would like you to determine the electric field caused by a spherical cloud of electrons with a volume charge density of -1 nanocoulomb per meter cubed. So this is a negative cloud. It's not a positive cloud. Density is negative. And of course, to be consistent with the notation of use, this one should be called rho v. It's a volumetric charge density. And here the radius of the sphere is 1 meter, and we would like to calculate the field at 3, and -1 meters. So what we have to do, we have to determine the unit vector pointing from the center of this sphere to this observation point. We have to determine the distance r from the center of this sphere to my observation point. I have to determine the total charge within this sphere. So I have to multiply this by the total volume to get the total charge q. So now if you draw this is your sphere. It has a radius of 1. This is a point 3, and -3. This is the unit vector pointing from here to here. We can tell that the length of this vector is equal to a square root, because it's a position vector. We took the center of the sphere as the origin. Square root of the sum of all the squares of the components. So 3 squared plus 3 squared plus -3 squared. So this will give you square root of 27. And the unit vector is simply the position vector of RP, the observation point, divided by the length of RB, which is square root of 27. If you put all this together, this is what we'll end up having. This is the total charge contained within the sphere over 4 pi epsilon r squared the distance between the center of the sphere to my observation point in the direction of r. What is q? Q is the volume. So here this is 4 over 3 pi r a cubed. This is the volume of the sphere, multiplied by rho v, the volumetric charge density. This is q now. This is the capital Q that we have. Divided by 4 pi, this is epsilon, unless otherwise mentioned. It is that of vacuum, of free space, 1 over 36 pi 10 to the minus 9. R squared, the distance, we agreed that r is square root of 27, r squared is 27. And this is in the direction of AR. If you simplify all this, 4 pi will cancel with 4 pi, 3 will cancel with 36 to give you 12, 10 minus 9 will cancel 10 to the minus 9, there is a negative sign there. So this will give you minus 12 pi over 27 multiplied by AR, and here I explained AR, expanded AR. So AR is simply the position vector of RB divided by square root of 27, which is really nothing but 3 square root of 3. 3 will cancel out from all the 3's in the numerator, and we end up here, if you divide, you get minus 8.806 in this direction. Okay, so this will be the direction of the electric field. That this answer makes sense? Yes, because this is opposite to the position vector, because the sphere has a negative charge. It doesn't have a positive charge. So that it's actually trying to attract any positive charge towards it. One other thing I want to mention is how to program this in MATLAB. If I give you any arbitrary volume and it has a variable charge density, the charge density here is more than here, the darker the area, the more the charge density. How can you get the field at any arbitrary point with position vector r. In the same way we did it for the surface case. You have to determine the point, divide your structure as shown here into small volumetric elements. They can be cubes, they can be tetrahedra, they can be anything that you want, and determine the vector pointing from the center of your element to the field point or to the observation point. So if this one here is called Ri, this center is called Ri, so this vector here is nothing but R. This vector Ri is equal to R minus Ri. This is a vector pointing from here to here, and you treat every one of these elements as a point charge. And then the expression for the electric field coming from this ith element is nothing but the charge of this element, I will call it here dq, over 4 by epsilon modulus Ri squared, the distance, multiplied by Ri. This gives you a vector. In order to sum all the contributions, you have to determine by the contribution coming from all other elements to that point. So in MATLAB or C or whatever, you do a summation over all I from 1 up to the number of elements, DEI. And of course, the smaller your elements become, the more accurate this summation will be, and the more accurate it will approximate the integration that we are doing for a continuous distribution.